In this lesson, we'll examine the application of panel data methods through a case study implemented with R. First, we'll introduce the case study. Then we'll load the data, visualize it, and explore it for various properties. We start the analysis by fitting the OLS and discussing the issues with OLS estimation of panel data. Next, we apply least square dummy variable approach and see how estimates improve. Subsequently, we'll apply time and individual fixed effects and compare the results. We'll also see how to extract these fixed effects. We'll also compare the first difference estimates with fixed effects estimates. Next, we'll fit the model with random effect. We'll also examine whether random effect or fixed effect is the suitable model using Hausman test. Next, we'll conduct error diagnostics, and lastly, we'll perform statistical inference using robust standard errors. In this video, we'll introduce our panel data case study on prediction of broad market-wide index returns. Broad market-wide indices such as Nifty 50 are one of the most advanced and sophisticated form of portfolios, very well diversified portfolios. These broad market-wide indices are known to reflect the growth of economy and are often correlated with macroeconomic factors such as GDP. Therefore, the strategy to invest in market-based on forecast related to factors such as GDP has become a very prevalent strategy known as factor investing, that is, investing in market based on predictions related to GDP. The idea is that GDP has a fundamental relationship with these broad market-wide indices, which essentially reflect the economic activity in a country. However, this exercise may be vitiated if the data is of multi-country panel data. Then this exercise may be vitiated by the unobserved heterogeneities, as we discussed in the theoretical discussions, such as country-specific factors. The data employed in this study is of the panel form and is used to forecast market index prices or returns. So we have serial numbers, we have countries, year, GDP, and return values. These values are scaled, so they do not reflect exactly the GDP or return values, but they are scaled to suit the case study. Using different panel data methods, we will examine the relationship between GDP and returns. We'll try to model it, and in subsequent slides, we explore the problem statement. We'll try to perform the following set of tasks. First, we'll try to visualize the data. We'll plot the year-wise market index returns for each country. We'll also plot year-wise GDP for each country, and we'll try to make use of box plot to show the heterogeneity in GDP and returns across countries and years. And we'll try to infer whether indeed the distribution of returns and growth of GDP over the years differ across country to country or carries heterogeneities across countries. We'll try to model the relationship of GDP with broad market-wide index returns, first using simple pooled OLS, and we'll try to infer what are the problems with this kind of approach. First, through visual approach, we'll try to see how the fitted line appears vis-a-vis actual data. Then we'll follow the least square dummy variable or LSDV model approach and model this relationship between GDP and index returns after adding country-wise dummies. Next, we'll convert the data into panel format in our environment with country and year as data identifiers or index variables. Then we'll model the data using fixed effect, using individual time and two-way, both individual and time effects. We'll perform the test of poolability to see whether the fixed effects are indeed significant or pool model is a decent model. Next, in case we find the fixed effects are indeed significant, we'll try to extract these time and individual fixed effects from the modeled fixed effect object from the panel data regressions. We'll also model the data with random effects, and we'll examine the output and comment on individual and idiosyncratic heterogeneity. We'll also comment whether random effect transformation is closer to pool or fixed effect. If you recall, whether lambda equal to 1, then in that case it is closer to fixed, or lambda equal to 0, then in that case it is closer to the pool model. We'll also conduct tests such as Hausman test to examine whether random or fixed effect model is more appropriate. Lastly, we'll examine the cross-sectional and serial correlation in errors for different models such as pool, fixed effect and random effects model. And then we'll also examine the homozydicity and heterozydicity related issues in the errors. That is, we'll perform error diagnostics. And lastly, as a solution, we'll use robust standard errors to estimate coefficients that are robust to error autocorrelations and heterozydicity in the model. To summarize, in this video, we discussed the case study. We discussed how first we'll visualize the data and see whether panel data methods are appropriate or not, and then empirically we'll examine different models such as pool, fixed, random effects, and also first differences and see their goodness of fit. We'll examine and perform residual diagnostics, such issues such as cross-sectional and serial correlation errors and heterozydicity. And lastly, we'll using robust standard errors, we'll try to perform statistical inference for these models. Let us start our implementation of the panel data case study. First, we'll set the working directory. As usual, we'll go to the session command, set working directory, choose directory, and we'll choose the appropriate directory where our data is available. I'll click on open. You'll notice a command has appeared on my console window. I'll take up this command and paste it here. So notice as soon as I set my working directory, you will find some of the data files appearing on this files tab, and I can read data from here. Now, as a starting point, first let us load the relevant packages. So we'll load the relevant library packages. In this particular session, we'll be using car library. Then we'll also be needing ggplot2. We'll use PLM, and we may also use the T-series package. So these are some of the packages that we may require. Now we need to load the data. So we'll read the data. We can already see the data file. So the most easiest way to do is to click on these data files. So for example, we have a file in CSV format. I can click on import. The data file appears on my screen and we can see how it appears. We can see the shape, country, year, GDP, return. We have already discussed the data. Let's name it panel. We'll name the data as panel data, and I can click on import to read the data. That is one way to do it. I can read the data. A command appears on my console window. For future reference, I can copy paste this command, and also a brief view of data appears in this window. So I can close it. I can paste these commands. Also, I have put the data in my file as RDS format also. So I can click on this RDS format, and then also I can click on OK to read this data. So that is also another way to read the data. I can select the file name as I wish, and a command is run, which I can again copy paste for reference. And this is also, please recall, for R this arrow symbol is same as equal to or assignment operation. So I can very well use this equal to symbol. So I have the commands as well ready for me. If I have read the data correctly, then I can just have a quick look at it. For example, I can see the summary of this data through the summary command. That is one. I can also run the brief command to have a look at the brief of my data. So I can check what is there inside data. So I can check the brief command, some of the initial variables. So first I have the country variable. So country is a factor variable. Then I have years. So it's a panel data basically. I have GDP. So GDP data is slightly scaled to suit this exercise. So you may not find it as regular GDP number. So it's slightly scaled number, and similarly I have return number as well. To summarize this video, we read the data, we loaded the relevant packages, we have set the working directory, and now we are ready for basic exploration of our data through visualization and some other exploratory exercises. Next, in a series of videos, we'll try to visualize the data through various important visualizations. Let's start with a simple scatter plot command. This is available in our car package, CR package. So we'll use this scatter plot command. First, we'll visualize return with year, the movement of returns with year, and we'll distribute the observations across countries. So we'll write this country, and command will be with this pipe symbol, country. We'll write data as panel data because our data name is panel, and we'll put this smooth argument as f so that there is no confidence band provided. So now we'll run this command and the plot should ideally appear on the plotting window here. As I run it, you can see the plot window. The interesting thing about this diagram is that the lines show the relationship between return over years for different countries, and each country the scatter points are there. You can see different shapes, and also the line is given in the form of different colors. Notice the interesting thing that for each of the country we can see the pattern of GDP and relationship. The relationship has over the years behaved differently for different countries. It's not the same for all the countries, and that creates kind of heterogeneity in this relationship across countries. So this is the first step. Next, now that we have seen the return movement of return across countries, we have seen that it's heterogeneous. In the same fashion, very same fashion, we will also see the behavior of GDP as well. So we saw the return and now we'll see the behavior of GDP. I simply paste the command, I will not rewrite it, and I'll run the command. Again, very interesting thing, we can make an interesting observation that GDP has also behaved in a very heterogeneous manner. For example, for some countries, many of them it is increasing, but there are few of the countries where it is decreasing as well. So there's quite heterogeneous behavior of GDP across countries. Let us also use the ggplot command to visualize the box in the box plot form. Box plot is a very usual sort of very interesting and useful way to visualize univariate series. So we'll make use of box plot through this ggplot command. We'll use the ggplot command. We'll supply the data, which is panel data, and aesthetic argument we need to provide, which is on x-axis we have GDP, on y-axis we have, so because this is univariate series, so there's no y-axis, we'll group the data across country. So I'll use this country as a grouping variable. So very nice, in a very nice way, the data will be grouped across countries. And fill, we'll use different colors, so we'll use the color according to country. And now let's add the geom argument. While the data will be printed now itself, I can print my data here itself. However, let me show you first what exactly I mean by that. So for example, 2 layers of my code is complete, so I can very well print the data. We'll not discuss it now. You can see here, we'll slightly make the plot more aesthetic with some more arguments, as we'll see. So first I'll add the labs, access lab labels. First is the title. I'll use heterogeneity across countries. So this is my main title heading. I'll give the heading for x-axis. Let me just minimize the plot window a little so that I have some more space. So x equal to GDP. So on x-axis I have my GDP. This is third layer I have added. Next layer I'll add theme. So I'll just specify some more properties of the plot. So for example, first the title. So there's a very interesting command, element underscore text, which will help me choose the font and size. For example, horizontal adjustment of the title size is 0.5, so it will be sort of in middle. I'll put the font as bold, so font is dark bold, and I'll also decide its size. The size may be 18, so it's slightly higher than the axis titles. Similarly, in a very similar manner, I'll specify the axis properties. For example, I'll use this axis dot text, and again the same element underscore text argument. So I'll just copy it and choose some arguments. For example, I'll use the size as 16, so I'll use the size of 16. Font I'll keep as bold, so it looks more sharp. And the last layer I want to add is, sorry, not the last layer, but the last argument here I want to add is axis.title. So I can first I change the properties of axis labels, and now title also. I'll use the element text, same element text again, and I'll give the argument, same arguments I'll use. So now I'm ready to plot. So let me just slightly enlarge the plot window. Let me show you how it appears when I nod. So we can see a very interesting plot will appear now. So you can see here. So now in this plot, box plot is a very interesting and useful way. Each box, if you notice, each box is a set of certain parameters. For example, the upper and lower ends of this box
is basically the 25 and 75 percentiles, Q1 and Q3. The median line is like 50 percentile or median point, which is at the mid of this box. The ends are whiskers. These whiskers represent sort of range. You can say is, for example, from 75 percentile onward you will find a whisker, and 25 percentile below you will find a whisker. These are the range of the data. And then you have certain extreme outliers pointed in the form of these dots. So these dots are extreme outliers. Generally, these whiskers are those points that are within certain range of 75% and above and 25% and below. And what is this range? This range is basically called interquartile range, which is equal to the distance between this 75 and 25 percentile. So this is the interquartile range, and this interquartile range is extended from the Q3 point here on the upside whisker and below Q1, which is the lower side whisker, and beyond this you have extreme outliers in the form of these dots, as you can see here. If we examine this box plot, we can see that across countries, we can see our data across countries, there is a lot of heterogeneity in the GDP data. So there is a lot of heterogeneity in this GDP data. Similarly, I can also just add instead of GDP, I can add my return variable here and see the distribution of return as well. I'll just type here return. I'll again enlarge my plot window so the plot is appearing nicely. And again, I'll not describe the box plot properties again, as we have done it already, but you notice the distribution of return across different countries is very different, very different. So this gives some idea that there is a considerable amount of heterogeneity across countries, and this gives us some intuition, although we'll see empirically as well. This gives us some intuition that if we model them simply by pooling all the observations together, the results may not be accurate. Now, for your report writing and other purposes, you can use this export command to save the data as image. You can change the format, PNG, JPEG. You can change the width and height, or you can do through dragging through mouse cursor here. You can drag the chart, get it in the right shape, or also you can use this export command to save it as PDF or copy to clipboard. For a detailed examination, you can zoom it as well. So that facility is also available to zoom it and have a good look at the plot. To summarize, in this video, we saw how to visualize the data, the relationship and evolution of return and GDP variables, and we also saw their distribution through the box plot. In this video, we'll perform ordinary least square regression by pooling the data, or rather pooled OLS regression. So we'll conduct the pooled OLS fitting or regression of the data, and we'll see what are the issues with it and how it can be misleading while working with this kind of panel data. So to perform this, we'll create a OLS variable which will store the output of the linear model, LM for linear model regression. Return is our dependent variable, GDP is our independent variable, and the data that is used is panel data. Now the output is stored here. So if I summarize this OLS variable, as we'll see, you will get the output, and in this output, as you focus, you'll find that the GDP coefficient is appearing as insignificant, which is very counterintuitive, because generally you would expect the GDP to have a significant role to play in the broad market-wide index returns. However, here it seems that GDP is not very effective. First and foremost, let us see the problems with this. So I'll use this plot OLS command to see some basic diagnostics. So I'll run this plot OLS, and after that we'll see in a more comprehensive analysis. But first we'll plot this OLS, and it asks me to press enter. So the first plot, it sort of plots residuals versus fitted values, and you can see the very poor fit, and also the variance of residuals is not very same across observations. So it's a kind of indication that there is a lot of heterozygosity in the data, and also the fit is very poor. Also, you can see the QQ plot, although QQ plot suggests that many of the observations that in QQ plot you compare two distributions. For example, here we are comparing the distribution of standardized residuals with theoretically normal quantiles or normal distribution. As you can see here, at some places there is deviation. So for example, it suggests that residuals are not exactly normally distributed. And if you remember, one of the important assumption in regression, OLS regression of this kind, is that residuals are normally distributed. Higher the deviation from normality, poor the regression model estimation. Also, you can press enter and you can check the scale location plot. The scale location plot suggests the You can see some of the outliers. You can identify the outliers, for example 44, 31, 51. These are some of the outliers which may affect your estimation, vitiate your estimation. So if you want to make a proper estimation, you probably you would do well by removing these observations. Although to highlight that in this case the magnitude of this, there's not much this thing. So for example, this plot also gives us some idea about homoscedasticity or heteroscedasticity of the data, because error variance is not same. So you can notice the distribution of residuals is not same across fitted values. So this is another way to have a look at sort of heteroscedasticity in the data. The last clause is very important because it gives us idea which observations are truly influential. Well, there may be some extreme outliers as we could identify in some of the previous plots, but here you can directly see the influential observations. And although it appears that observations number 22 and 23 and so on 11 are slightly more influential, but the nature of this plot is we do not see the Cook's distances. So generally, customary this plot, you will find the lines corresponding to Cook's distance of 1 and 0.5, and those points that are beyond those lines, they would be slightly extreme. In this plot, I do not see those Cook's distance that are 1 and 5, so probably the Cook's distances are rather small. Let me have another way to examine the Cook's distance, probably to get more idea why this we do not see those two lines. So let me summarize the Cook's distance for this particular model, and as we can see, it's all the maximum Cook's distance itself is like order of 0.1. So that is why probably we couldn't see the higher Cook's distance of 1 and 0.5. As a practice, whenever you see those lines will be shown here in a sort of dotted form like this, and when you see those lines of 1 and 0.5, you gather that those are points that are beyond those lines are extremely influential and affecting your regression. The last step in this video we'll do is we'll plot a GG plot, and we'll see how the average aggregate plot is appearing as compared to the other individual country plots. So we'll first, as a first step, data aesthetic command x equal to GDP. So we want on x-axis we want GDP, on y-axis we want returns. We'll group our observations according to country. So for that, this grouping according to country, and we'll also color the observations, the lines, individual lines according to country, so that we get a nice colored. This is the first layer of our GG plot. The second layer is the point. So we'll also plot the points through this geom point command. And the third layer to this is geom smooth. So this geom smooth will ensure that we have a line. So we'll get the line, and I'm specifying the method as lm. So this method equal to lm will ensure that the line is a straight line, and I'll also put a standard error as false. So this s equal to f false argument ensure that there is no confidence band that slightly vitiates the graph, creates hazy graph which is difficult to visualize. So now, so we have added the individual country lines, and now we'll add this abline command. I'll add the OLS model here, the aggregate line. So how to do it? I have already fitted the aggregate OLS. I'll make use of its intercept, which is this first, and then also its slope, which is equal to this. So this is my slope 2, and I'll put a line width of maybe 2 and color of lead, so it comes out sharply. So this is my remaining next step. Now, while the plot will be appear, I can show you a brief glimpse of this plot, but in order to make it aesthetically more appealing, I need to do some addition to it. So let me run this plot. Let me see if it is working, and we'll just have a glimpse of this plot, but I want to add some aesthetic. So the plot is there, but still I need to add some, from aesthetic purposes, I need to add some more layers, as you'll see. So first and foremost, I'll add this labs command, and in the labs command I'll give the main title of the plot, which is heterogeneity across country. So this is my central title, and my y-axis, I have my y-axis as returns. So the next layer I would like to add is the theme layer, and probably I'll pick up from the previous set of codes. I'll not rewrite the code. In the interest of time, I'll just pick up from here, and same set of probably I'll do with the same set of arguments, so I'll not change them much. Let me run the full command and you'll see a nice plot appearing here. So I'll just enlarge my plot window and now it is there. So in this plot, you can very nicely and clearly see the individual lines for countries A, B, C, D and their scatter points also, which shows that there is a lot of heterogeneity. For example, the green one, country C, the green one is on the upper end while the lowest end is the D country D, dark green is on the lower D, and then you have some countries in between. And also the relationship between GDP and returns are not homogeneous across countries. There is a lot of heterogeneity in the relationship. And the average fit, if I would have done the average fit, it would have come as red line. So obviously average fit would have indicated poor sort of vitiated because of this individual heterogeneity across countries. So probably it's not the right way to estimate the relationship. So in this video, we examined the OLS fitting or the pooled OLS fitting of the panel data. We found not only visually but empirically as well that due to unobserved heterogeneity or individual heterogeneity across countries, the relationship estimation is vitiated and probably not a very good fit, and not very accurate estimates are obtained. So we need to make use of panel data methods that we have discussed earlier. In this video, we'll start with a very simple version of panel data model, which is least square LSDV, least square dummy variable method. We have already discussed the theoretical aspect of it. To implement this method, the least square dummy variable method, let us call it LSDV model. In the LSDV model, all we'll do is simply use this LSDV. Let's store this object here LSDV, and we'll use the linear modeling. Not much change there. So we'll regress our return variable on GDP plus. Now the only addition in the simple OLS we'll do is we'll add the factor as country, and then I'll add the data as panel. And now when I summarize this model, notice something interesting will happen. When I summarize this model, R will automatically add the dummy variables. If you recall, we need n-1 dummies. So the country A, R chooses the dummy alphabetically. So the country A is loaded on this intercept variable. And we can see now in the output, we'll be focusing on the coefficient of this GDP variable, which has now become significant at 90% confidence. So it has become significant at a significance level of 10%, or what we call as confidence level of 90%, which shows that when we explicitly accounted for the individual heterogeneities, country specific heterogeneities, then our model shows some clarity, or some clarity has emerged with this GDP variable being significant at 10%. So with this, we find that this LSDV method of panel data estimation gives us some intuition that probably these individual heterogeneities were indeed creating some vitiating effect on our simple pooled OLS estimation, and therefore it is more desirable to look at panel data methods to account for the unobserved heterogeneity. In this video, we'll continue with our examination of panel data relationship. First, we'll declare our data formally as a panel data with our environment. And second, we'll see whether these fixed effects are significant or not. So we'll start with the examination of panel versus pool. First, let us explicitly tell R that our data is a panel data set. And for that, we'll use this pdataFrame command in the PLM package. We'll tell that our data panel index equal to C country. So first is the country individual index and then time. So now we have told, let's see, and whether your data is converted into panel data or not, you can run a head command, and you can see here now there's a specific dimension which is added. It's not a column, it's just a property of your data itself. Like a timestamp, you have a time and individual dimension. You can also add a summary command to see more clearly panel.set. So you can see your data has been summarized properly across country and year dimensions. Now let us model the simple fixed effect model. Now, so we'll model fixed effect with individual heterogeneity. So only individual heterogeneity is accounted for in this fixed effect. We'll use PLM command, return GDP tilde. So very similar format. Data will describe as panel.set, and model within by default runs individual effect. So by default it runs individual effect if you do not specify any effect. If I run the summary of this fixed.individual, notice in the output the GDP coefficient is very similar to what we got with the LSDV method, and also its significance is also similar at 10%, that is 90% confidence, which is very similar to what we got with LSDV. So that means the fixed effect has accounted for the heterogeneity and results are similar to LSDV. There is a very simple and interesting way to perform pooled OLS also within panel data framework PLM package. I can write pool and it will give me the, let me call it pool, and this pool model will be very nicely run with PLM rather than earlier we were using LM, but now we are using PLM and it will be very nicely run. Now we can see the output again with pool, as we have already seen the results are not significant, that we have already seen. But more importantly, with this pool object in PLM environment, we can compare, we can perform a poolability test in the PLM package for fixed effects. So I run pool fixed and fixed dot individual effects. So we can see the individual effects are significant. We reject the null hypothesis, this sort of F test which says that both the models are, there's no incremental benefit of adding these fixed effects. But here we can see that we reject the null and we say that indeed there are significant fixed effects by rejecting the null. So there's another way to conduct this test, which is the PF test, which will also help us. So we'll again type fixed and pool and we fixed.lm. So here so this should be fixed.individual, and again we get the significant effects. We reject the null hypothesis of no individual effects. Indeed there are individual effects. We also, so there's also something called PW test for the same, and we can perform PW test of significant effects, and for all these tests we get the significant effects, unobserved individual effects. Now as of now we have tested for individual effects, but we can also test for time effects. For example, the way to do it, very similar set of commands we'll apply for time effects. How to do that? So we'll run the command fix.tm. So I'll use, since we are using time effects, I'll use fix.tm, and here all I need to do is put effect test time, effect equal to time, and when I run it and I can check the summary. Okay, so this model probably is not so good. We get PR equal to insignificant value is very high, so it's not significant as we can see. So that means time effects are not very significant. In fact, you can further cross check it with the same set of tests. Here instead of this I'll use TM. So we'll check, no. So I can run all sort of tests on TM. Yeah, so it's not here as well. So I can see that time effects are not significant. Now that we have tested with time effects, let us test with two ways, both time and individual. So when I run the two ways effects, it's also not very difficult. I can run here instead of time, I can put two ways. Sorry, so I need to put it, I'll put it TW. So let's give it a name TW and let's see what is the output. So when I run with two ways, I can see the output. You can see again, so GDP is not turning to be significant, so that is slightly problematic, which means time, somehow individual effects was the best fit model. Let us compare it with the pool model. So we see that with pool model, it says that significant effects, in both cases we are able to reject the null in given these p values, which means we are saying that effects are significant, but we have already seen that time effects are not significant. So the significant is coming from the individual effects. There is also a very interesting way to simply test this with PLM test. So I can simply use PLM test and it's very nicely conducted. PLM test and testing for individual, testing for fixed effects. So I can simply type here pool, and then you can test for the effect which you want. For example, you can specify the individual and you can run it. Yep, they are significant. The version of test here is Honda. You can change the test. You can type question mark PLM test and you can select the relevant test here. For example, there are multiple tests available, Honda, BP, GHM and so on. So you can test multiple tests as well. There's nothing wrong with that. So individual, I can test for time. Let's see what is the result for time. Not significant. So now you know that when I run two ways, it's without even running it, we should know that it may be significant, but the significance is derived from the individual effects. Two ways are a sort of combination of time and individual. Because we are getting significant effects, they most probably they are coming from individual effects, and time effects are not so significant. To summarize this video, we examined the fixed effects for individual, time and both individual and time two ways effects. We found that there are indeed significant effects, and these significant effects are coming from the individual unobserved heterogeneity aspect of the data. In this video, we'll examine how to extract the fixed effect that we have modeled. So we'll examine how to extract the fixed effects, both time, two ways and individual. So let's start by extracting with this fixf command, fixf. We will use this. We have already taken the fix dot individual effects, and we'll specify that we want to extract the type level. So with this level command, we'll get the fixed effects at level. Something interesting, we have already extracted the LSDV model. I'll show you that we have already done the LSDV model, and I'll show you that there's a relationship between LSDV dummies and the levels fixed effect that we have extracted here. You can see that the intercept is loading the variable A, as you can see here. Similarly, I can add up this fixed effect at level by adding this intercept to this fixed effect which is at B to get this number. So basically at every individual country, it is the difference between the intercept and the level. So for example, at C, the effect is nothing, but if I sum this delta C 0.91 with 0.29, I'll get this number 1.2. So these are the differences. So these are the differences with intercept. Also, R allows you the flexibility to extract fixed effect at first difference. So there they are in the form of first difference that you can obtain. You can see they are exactly sort of identical. So A is not produced, which is loaded on the intercept, and other fixed effects are sort of identical here. In addition to first difference, you can also add mean, difference of mean, the mean, and there also you can get the mean number, average, subtracted from the averages of fixed effects. This is how you extract the individual fixed effects. Now if I want to extract the time fixed effect, again the command is pretty simple. Also, there's one more thing, you can check the significance of these fixed effects by summary command. I can put these fixed effects and inside the summary command to get the fix. You can see we get the fixed effect as well as their summary number, the significance. Similarly, I can get for time. So all I need to do is supply the variable tm, and I can get the fixed effect, and also I can get the summary number here. So here we are extracting the time fixed effects. So that also we can obtain. As you can see here, we can see their significance and other things. All I need to do is revise the command a little bit, and I can give you the summary, and their significance also we can obtain. In a very similar manner, I can also obtain the two-way fixed effects. All I need to do is just specify that these are two ways fixed effects, and we can find the two-way fixed effects. We can also summarize them, so it's pretty easy. I can just summarize the two-way fixed effects. All I need to do is put TW. All I need to do is this TW and summarize, and we can get the two-way fixed effect. In fact, I need to specify that effect is two ways. So I'll specify the effect as two ways. So here I'll get the two-way effects. You can see here the combined effects, two ways, or rather I'll put effect here as two ways. So I'll get the two-way effect here. So we can obtain the two-way effects also. So it's pretty easy. So in this video, we saw how to extract the fixed effects for both individual time and two-ways model. And we also saw the individual effects were pretty similar to the LSDV model, least square dummy variable model that we ran earlier, which is also intuitively thinking about the model, which should have been there as well. In this video, we'll learn how to implement first difference model, first difference panel data model. We have already discussed the theory. So I'll not rewrite the code, I'll simply borrow from the previous code. All I need to do is I'll give it a name FD for first difference, and all I need to do is I need to specify, instead of within, I'll use FD, and the same command can be used. So I'll run the first difference model. Let's summarize this and examine the output of this first difference model. Let's see how it appears. So notice the output is pretty similar to what, in terms of its coefficient of GDP and its significance, it's very similar to the LSDV as well as fixed effect model. So we can see the significance is around 10%, which means 90% confidence level, and a coefficient which is also very close to, we had around close to 0.039 or something with the fixed effect and LSDV model. It's very similar. So we get a very similar result from FD, fixed effect, and LSDV models. This is very intuitive and similar to what discussed in the theoretical part. In the next video, we'll discuss random effects model. In this video, we'll see how to implement random effect model. Again, I'll not write the full code. I'll just borrow it from the fixed effect model, and we'll implement the random effects. We already discussed the theoretical part. So the code is pretty simple. Let's name it random, and I'll specify here the random. Now let me state at the beginning itself that this is individual effects, because we have not specified any particular effect. So it's individual effects, summary random. So I'll just run it. So let me run the model. So now, interestingly, in this model, there is one additional aspect in the output, and you can choose the particular effect, particular model that is run. For example, as of now, Swami Aurora, which is the default version, but there are different models available to check. Notice in the effects, because this is individual, you can see only individual effect, which is pretty high as compared to the idiosyncratic part of the variation. The individual effect is pretty high, around 62%. So it indeed seems to be important. The lambda we discussed in theoretical discussion is same as theta here. That means almost it is closer to 1. So that means it is the random model is closer to the fixed effect rather than on the band or spectrum of effects. It is closer to fixed effect rather than pooled, which is also confirmed by this theta parameter, which is same as lambda in our discussion. And notice the GDP coefficient, which also very close in terms of significance, and its effect is very close to what we had with fixed effect and LSDV and FD. So it gives us some idea about the consistency of our results. Now, in a very similar way, we can include time fixed effects. For example, if I want to, let's name it individual, random individual. Rather, to make a distinction, I'll name it random individual. So this is our random individual model that we have run, and then I will run with time effects. Let's see how it appears. So instead of, so I need to add one more parameter, effect, as time, and here I'll specify as TM. So it will give me random time effects. Let's see what is the nature of output. Now here in the previous part, here notice the time effects are explicitly loaded, and it seems when I load the time effects are not significant, and even theta parameter is 0, which says that our random model is closer towards pooled OLS. This is due to the fact that this time parameter is not contributing any much to the explanatory power of the model, and model feels that better would have been if we would have used pooled. And this was expected already, because we have already seen in the fixed effect results that time effects are not contributing much. Let's see what about two ways. So we'll use the two ways effect, two ways, and it's very easy to implement. I can write this two ways command here, and let's call it TW, random TW, and interesting output will be generated. As you can see now, another dimension apart from idiosyncratic, you have individual and time, and as we expected, the individual dimension is pretty large in terms of contribution to variation, around 63%. Theta is also important when we have individual effects. It is getting diluted with time and two ways. So that means time, indeed, in fact, time and time effect is diluting our overall effect part, and therefore it is better to keep only individual effects where theta parameter is pretty high and closer to the fixed rather than pooled. Again here, because the time effects are vitiating, our model has slightly lost its power. So we'll, as a model summary, we'll stick to our individual effect. Now, if you recall, whether to use random or fixed, we relied on our Hausman test, and the way to perform Hausman test here, we have already had a great detail about theoretical discussion about Hausman test. So here we'll only talk about implementation, which is very simple in R. So I use PH test for Hausman. If you want to know more about what are the parameters and arguments, you can simply type $PH test, and you'll see a lot of details appearing here. So a lot of details you can test here. But for simplicity, all I need to do is supply fixed effect. I'll supply fixed dot individual and also random, because both of these models are good, random and fixed individual models. So I'll run them, and I'm not able to reject the hypothesis. Now this is slightly interesting. The model suggests that we are not able to reject the null, that both of the models are consistent. When both the models are consistent, you go ahead with the random model, and in this case it seems random with individual effects is a good model, so we go ahead with the random model. But if you recall, random model was had a parameter of theta equal to 0.76, which was indeed very close to fixed effect. So whether we are using random individual or fixed individual, we are getting similar results, which is good for our experiment, which confirms, or rather in research we use something called weight of evidence approach. So we try different models, and wherever the evidence is pointing more, we tend to choose that. So let's say if you have 10 models and 8 models are pointing towards a particular result, then probably that result is more accurate. And in this case, both fixed, random, and indeed LSDV and first difference models are pointing towards the coefficient of GDP in its relationship, which is closer to 0.003 or 0.0035, and a significance level which is around 0.01, which 0.10, which is 10%. Let me show you the outputs in fact. So if I summarize the outputs, you will recall that our fixed individual, this 10% significance level and 0.0039. Similarly, if I summarize random, so I get around similar result. I summarize LSDV, I also get a very similar result. And lastly, if I summarize FD, first difference, then also I get. So it's a very resound, kind of very solid result. We can say that almost identical for all the models, around 0.004 or 0.4% coefficient. So it's a very sounding, and we should be happy about this, that we are getting a very consistent sort of result across different models. So to conclude, we saw that results, while the overall Hausman test suggests that it should be random model which is more accurate, but looking at the output, we find that all the results are consistent, pointing to a GDP coefficient of 0.004% and a significance level of 10%. That means a confidence level of 90%. And also we found from the theta parameter, or what we also call as lambda parameter, the random effect model is closer to the fixed effect rather than pooled OLS on the spectrum of effects. In this video, we'll examine problems of serial correlation, cross-sectional correlation, as well as heteroscedasticity in error terms. So we'll start with the examination of serial correlation in error terms. Serial correlation in error terms. And this will also help us decide between fixed effect and first different model. For example, to start with, you can try with this simple PWFD test of serial correlation in FD model. So if I supply the model, which is FD model, it tells me that FD model errors are indeed serially correlated, which suggests that FD model is probably not a so good model. If errors from the FD model are serially correlated, then better to go with FE, fixed effect model. But still, let's test if errors from FE model are serially correlated or not. As expected, they are not. Then another way to test this, which is called PWAR test, where you can supply your fixed effect model, and fixed effect model errors are not serially correlated. So overall, these results suggest that between FD and FE, because, and we discussed in the theoretical part also, because the errors of FD model are serially correlated, it is better to go ahead with fixed effect model. Next, let us look at the cross-sectional dependence in error terms. Cross-sectional dependence. So if there is any cross-sectional dependence, which will be highlighted by the cross-sectional correlation in error terms. The way to perform this test is also quite simple. So let's start with our fixed effect model. There's something called PCD test, and we'll supply our fixed dot model, which is the best fit model, and we'll use the test as LM. So we'll use the LM test. Let's start with the LM test. And there seems, we reject the null, and we find that indeed there is some cross-sectional dependence in the fixed effect model. There is another, apart from LM, we also have CD test. So patient CD test. Earlier we had Bush Pagan LM test. Now we can also perform CD test. But CD test sort of rejects the cross-sectional dependence. So we have a mixed sort of result. We can also perform this on the random model. So for example, we can also perform this test on the random model, let's say, and there is random model as per LM test, there is some correlation. Let's perform the same on CD test as well. So CD test says that there is no correlation. So here we get a sort of mixed result in terms of cross-sectional dependence. However, in our previous examination, we have already well settled that the model to go ahead is all the models are giving similar results, but the two best models are fixed effect with individual effects and random effect model with individual effects. The last test that we wanted to conduct on our error was about heteroscedasticity. So we wanted to conduct heteroscedasticity, whether our errors are heteroscedastic or homoscedastic. So let's see. Very simple BP test is available. So that would require library LM test. If we have not loaded, we need to load LM test library, and in the LM test library we'll perform this BP test, and we have return GDP as a variable, and let's add factory. Let's add the effects. So effects are country specific effects we'll apply, and after applying for country specific effects, let's see how our errors behave. In our data panel, we'll put student equal to F, and our BP test suggests that significant effects, heteroscedastic effects are there. So it seems heteroscedasticity is there in our error after accounting for these effects explicitly. So how to deal with this? So to summarize, in this video we saw that there is some evidence of cross-sectional dependence and also heteroscedasticity. So how do I correct for these correlation error terms and heteroscedasticity in my coefficients, and correct the coefficient matrix for proper hypothesis testing? So in the next video we'll see to compute robust standard errors that will be employed to compute appropriate hypothesis testing, t-test and statistical inference. In the previous video we conducted residual diagnostics, and we found that our error terms were afflicted by problems of correlation, cross-sectional correlation as well as heteroscedasticity. So in this video we'll examine robust standard errors, a very interesting and ingenious way to deal with these error problems. So this would require library LM test, and what we'll do is let's start with a simple coef test function. We'll supply our random model first. Let's see if random individual model, and the error we'll choose is VCOV HC. So this is the corrected matrix for random model, which is corrected for heteroscedasticity related correction. You can also, in the same model, and you can see this is the correction for heteroscedasticity. Similarly, you can correct the fixed effect model as well. Let's correct the fixed effect model results. So coefficients will not change, only the significance and t values, because this robust standard errors will collect for standard error. So, and t value is estimate divided by standard error. So the t value that you get is corrected because of the standard adjustments to standard error, and accordingly the probability value, the p value will also be adjusted. So let's do the same correction for our fixed effect. So there's a slight decrease in the power of test, as you can see, because probably we were getting some more favorable results because of heteroscedasticity and so on. So that is now corrected for. Similarly, we can run the pool thing as well. Let's see, pool. So the pool results, although pool results are not so meaningful in this case, we are working with panel data. There are some more advanced version of robust standard errors. Let's start one by one. Let's focus on fixed effect, and similarly you can apply random, but we'll start with fixed. So let's say we have fixed individual model. Then we provide a slightly more advanced version of this variance covariance error term. So for example, VCOVHC, this is our variance covariance heteroscedasticity consistent matrix. But here the method that we'll use, there are different methods available. For example, you can choose white to white's correction, and you can specify the type, the kind of type that you want to use is HC3, and you'll get a slightly different modified result. So here I can run this. Let's run this and see if we get the result. Yes, and now with this adjustment, significant level has improved a lot. Similarly, there are different versions for this. For example, you have, apart from this, you also have Arellano method. You can apply, and then there are different versions. For example, instead of HC3, I can apply HC0 or maybe HC1. So different ways to correct for this thing. Similarly, you can change for Arellano also. I can change, this is White's method, I can change for Arellano also. Let's see if there exists HC0 for Arellano. Yes, it exists. We can check that. Also, if you want to check what are the options, you can run this question mark and you will get in the help window, you can see what are options available to you. So there are Arellano white 1. So the options available to you are Arellano white 1 by 2, and there are different types HC0. If you want to read more about these, you can just have a look at what exactly these error terms mean to you. You can read in more detail about all the literature. But the point that I wanted to highlight here, there's also a way you can cluster errors. For example, you can cluster across group or time. For example, we realized in our case, time is not such a major problem, but clustering across group is a problem. So the way we can adjust for it, I'll not rewrite the code, I'll make a small adjustment. So what we can do here is, we can specify the method as Arellano, maybe type as HC3. You can choose different type, but then you can do clustering. You can change the clustering methods. For example, you can cluster, and you can cluster across groups. So because in our case we realized cross-sectional dependence was a problem, so you can cluster across groups. But also, although time was not a problem, but you can also cluster across time as well. So that also you can do. And now another thing, you can change these methods. For example, instead of Arellano, you can use maybe white 1, and so white, so we have in white, we have white 1 by 2, so we'll use white 1, maybe HC0, and you can read all the interpretation about these white methods and so on in the description help menu. So we can see the coefficient significance. Broadly, our results are pointing to the same coefficient. We have done number of permutation combinations, so broadly our results are pointing to a coefficient value closer to 0.4% with a significance level that ranges within 10% or better, so around 10%, and in some models it has improved as well. So broadly we get consistent results. So to summarize, in this video we examined the robust standard errors and how to implement them with R. We saw very different versions of robust standard errors, and we also saw how to cluster them across time and groups. So that is also we saw.
In this lesson, we examined the relationship between GDP and broad market-wide index data. For example, Nifty 50. Since the data has multi-country dimensions, it carries unobserved heterogeneity. We started the estimation with pooled OLS approach, which offered counterintuitive results. That is, there is no relationship between GDP and broad market-wide indices such as Nifty 50 and S&P 500. This leads to suspicion that unobserved heterogeneity may be affecting our estimation. We start our panel approach with least square dummy variable method. The results from least square dummy variable method show that there is relationship between GDP and market-wide returns. We corroborate these findings with fixed effects method. We find that indeed individual effects are significant but not the time effects. We also extract these effects and find that the effects observed with least square dummy variable approach and fixed effects approach are similar. Next, we employ the first difference approach and results similar to that from fixed effects approach are obtained. Lastly, we perform Hausman test which suggests application of random effect is more appropriate. Random effect approach also shows that the individual effects are more significant. The results from random effect approach are similar to those obtained from fixed effects method. Lastly, we conduct error diagnostics of the model. We correct for issues related to errors such as heteroscedasticity and serial correlation by using robust standard errors.